Okay. When it comes to graphing a rational function by hand, it could be a lengthy process. There's a lot of information that you got to break down. And then by putting all the information, all the pieces together, you can sketch the graph of a rational function, roughly. And it's just a matter of looking at it. And there are a lot of steps to it. I'm not going to lie. There are definitely a lot of steps to graphing a rational function by hand. But it's really not that bad when you look at all the processes you have to do. So to graph a rational function by hand, here's what you're going to do. Factor the function completely. So you're going to factor the top and bottom completely. And basically you're going to write it in lowest terms. Identify the domain of the rational function. Locate any x or y intercepts. Okay. You're going to determine the multiplicity of each x-intercept, which is the zero of the function. Determine if they're even or odd multiplicity. You're going to locate vertical asymptotes. Now, in addition to locating the vertical asymptotes, which, when you find the domain, basically you're looking for the vertical asymptotes at the same time. You're going to look at the multiplicity of the vertical asymptotes as well, because that's going to dictate what's going on with the rational function at the vertical asymptote. And you'll see what I mean when we look at examples. So you're either going to have one of two possibilities. If the vertical asymptote comes from a factor of odd multiplicity, then the behavior of the rational function on either side of that vertical asymptote will be inverted. So what that means is, if this is a vertical asymptote, x equals a is a vertical asymptote, and it comes from odd multiplicity, if it's odd multiplicity, then what that means is it's going to be inverted. So what I mean by that is the graph on either side of this vertical asymptote will either do this and this, or it'll do this or this. It just depends on the multiplicity of that vertical asymptote. If it's case 2, so if this vertical asymptote has even multiplicity, then the behavior on either side of the function will be similar. So what that means is the graph will either look like this, it'll be similar, or it'll be like this. Okay, so you'll see what I mean when we get to it, but that's basically what it will do. Then you're going to find the horizontal or oblique asymptote. You're going to determine if it crosses the function crosses the horizontal or oblique asymptote. And then you're going to bring all the information together. So you're going to put all this information on the coordinate system, and then you're going to sketch it by hand. It seems like a lot of information, but just take it one step at a time. And when I make these problems on an exam, I will break it down in a similar way. So don't worry about remembering these steps. When you're doing your homework, on the other hand, you might have to just follow the steps, but it won't be broken down this way on your homework because there's nothing I could do about that. But on an exam, don't worry, I will ask this question a similar way. Okay, so let's factor this rational function completely. So the numerator is x minus 1. Okay, that's factored. The denominator is x squared minus 9. That factors. That's a difference of 2 squares, which factors to be x minus 3 and x plus 3. Okay, so it's factored. What's the domain? Well, the domain is everything. It's all real numbers except what? When the denominator equals 0. So except when x minus 3, x plus 3 equals 0, which is the values. That's easy. That means x equals 3 or x equals negative 3. So my domain is all real numbers except x equals 3, negative 3. So that's my domain. As you know, in interval notation, it's going to be from negative infinity up to negative 3, not including it because that would give me 0 in the denominator, which I can't have. From negative 3 to positive 3, and then from 3 to infinity. That's an interval notation for the domain. Okay, locate the intercepts. So the x-intercepts, those are the zeros, right, of r of x. So we're going to determine the multiplicity of these when we get to it. So the x-intercept is when my function equals 0. So you're setting this function equal to 0. Well, when is that rational function equal to 0? You know, this is 0 over 1, right? You could cross multiply here. That's easy. X minus 1 times 1 is x minus 1, right? Equals 0 times x minus 3 times x plus 3, which is 0. That's easy. Just add 1 to both sides and you get the value x equals 1. So my x-intercept is the value 1, 0. In other words, that's the only 0 of my function. The only root of my function is x-intercept is 1, 0. Now let's look at the y-intercept. That's when x equals 0. That's easy. Just plug 0 into your function. When you plug in 0, you're going to get 0 minus 1, which is negative 1, divided by 0 minus 3 is negative 3, times 0 plus 3, which is positive 3. So negative 1 over negative 3 times positive 3 is negative 9. So that's negative 1 over negative 9, which is 1/9. So my y-intercept is 0, 1 over 9. And that's an ugly 1/9. Okay, so these are my intercepts. So let's keep going. And, you know, when we get to the point where we're going to graph this, I will rewrite all the information on that sheet. So locate the vertical and horizontal or oblique asymptotes, if any. And then I'm going to say this as well. Also, determine the multiplicity of the x-intercepts, which are the zeros, and the vertical asymptotes. So I'm going to be determining the multiplicity of the vertical asymptotes and the x-intercepts. Okay, so the vertical asymptotes in a way we've already done that. We already did that. You know, the vertical asymptotes are the bad points. Right? If we look back to problem number 1, you know, if we go back to the first part of the problem, the bad points here are -3 and +3. So those are the vertical. That's just work from number 1. So work from number 1, the vertical asymptotes are the values x equals -3 and +3. So those are my vertical asymptotes. Now I want to determine the multiplicity of those vertical asymptotes. Okay, so here's vertical asymptotes, multiplicity of vertical asymptotes. Okay. So for the value x equals -3, that comes from what factor? So that vertical asymptote, right, x equals -3, comes from the factor x plus 3. All right, that comes from the factor x plus 3. And the power of that factor is 1. All right, that power is 1. So that has a multiplicity of 1. 1 is odd. Which means, now, this is a vertical asymptote. This is not a root of the function. So if my vertical asymptote has, so right here, right, in the third step, if my vertical asymptote comes from a factor of odd multiplicity, then the behavior of that on the either side of that vertical asymptote is inverted. So that means r of x is inverted on either side of x equals -3. Okay, now let's look at the other value. For x equals +3. That comes from the factor. Oop, my camera is being weird. Come on. All right. So for the value x equals 3, that comes from, you know, x equals 3 comes from the factor x minus 3, right? And since the degree of that power is 1, it's the same thing as the other one. Multiplicity of 1, which is odd, which means that r of x is inverted on either side of x equals 3. So the behavior on either side of -3 and +3 is similar. It's inverted. It's similar in the fact that they're both the same. It's not similar like this, but it's a case of letter A. Right? They're inverted. So that means it's doing this or this on either side of that vertical asymptote. And you'll see what I mean when we graph it. Okay, so since I located the vertical asymptotes, I determined the multiplicity of the vertical asymptotes. Let me determine the horizontal asymptote. All right, so if I go back to my original function, remember, to determine the horizontal asymptote, you're looking at the degree of the top compared to the degree of the bottom. So the degree of the top here is 1, right? So the degree of the top is 1. The degree of the bottom, x squared, the degree of that is 2. So the degree of the top is less than the degree of the bottom. So that means I have a horizontal asymptote of y equals 0. Okay. Now I have one more thing to do here. I determined the multiplicities of the vertical asymptotes. Let me determine the multiplicity of the zeros of the x-intercepts. So yeah, I did say there's a lot of steps to this. Determine the multiplicity of the zeros of the x-intercepts. So the x-intercepts, there is only one. On number 2, the x-intercept was x equals 1. Okay. So for x equals 1, that comes from what factor? X equals 1 comes from the factor x minus 1. And x minus 1 is raised to what power? 1. So that means it has multiplicity of 1. 1 is odd, which means what? Now, since this is a root, or an intercept, remember when we looked at polynomial functions, if I have an odd multiplicity, what does it do at this value at 1? What does it do at this x-intercept? An odd multiplicity means it's going to cross the x-axis at x equals 1. It's going to cross x equals 1. If it was an even multiplicity, it would touch the x-axis at x equals 1. Don't confuse this one for that one. This one is just telling you it's crossing x equals 1 because 1 itself is odd. Okay? Okay. So those 4 things, vertical asymptotes, the multiplicity of the asymptotes, the horizontal asymptote, the multiplicity of the x-intercepts. There's a lot. There's a lot to do here. I'm not going to lie. Now I want to determine if my function is going to cross the horizontal or oblique asymptote. So remember I said that, recall that r of x can never cross a vertical asymptote, but may cross a horizontal asymptote or oblique asymptote. So how do you determine if it does? How do you determine if it crosses the horizontal or oblique asymptote? How to tell? Well, you just get to set r of x equal to the horizontal or oblique asymptote. That's all you got to do. If you get a value, then it indeed crosses it at that value. If you don't get a value, or if you get an incorrect statement, then it doesn't cross. So if you get a value for x then it crosses. If you don't, get a value for x, then it doesn't cross. All right. So my function, my rational function is, x minus 1 over x minus 3x plus 3. And I'm going to set that equal to my horizontal asymptote, which was 0. So if I solve this equation, no, I already did that, didn't I? I already did that. So if I solve that equation, I get x minus 1 equals 0, which means x equals 1. So, okay, that means my function r of x crosses the horizontal asymptote at the point 1, 0. And I know that because that point 1, 0 just happens to be the x-intercept. All right, it happens to be the x-intercept. So sometimes you might get some redundant information here, and that just happens sometimes because of the nature of these problems. Sometimes you'll get redundant information. You just got to check each case. You just got to check all the information. It's kind of like solving a puzzle. In order to solve the puzzle, you have to organize your information, and then you got to try and bring it together to graph this rational function. So sketch r of x below using this information. All right, so yeah, there's a lot of information here. So let's sketch it. I'm going to emphasize these lines a little better. All right, so let me list all the information. Information for the function, it was x minus 1 over x plus 3, x minus 3. So the intercepts were what? The x-intercept was 1, 0. And we know from the multiplicity test that it crosses at x equals 1. The y-intercept is the value 0, 1 over 9. There is no multiplicity test for a y-intercept. That always crosses. The vertical asymptotes are the lines x equals -3 and +3. We did the multiplicity for, well, the horizontal asymptote is the line y equals 0. The graph r of x crosses the horizontal asymptote at 1, 0, which is, happens to be the x-intercept, because the horizontal asymptote and the x-intercept lie on the same point. So that's okay, that's fine. Sometimes you'll get redundant information, like I said. Now now let's look at the multiplicity of the vertical asymptotes. We said what? X equals -3 is inverted, and x equals +3 is also inverted. All right. That's for the vertical asymptotes. Okay, so we identified the intercepts, the vertical asymptotes, horizontal asymptotes, multiplicity of the vertical asymptotes, the multiplicity of the x-intercept, and it crosses the horizontal asymptote at 1, 0. So we got all the information we need. So now we can graph our function, r of x, by hand. This is just a summary of all the information we did in steps 1 through 4. I know, it's a lot of information. I know what you're thinking. It is. But this is how we get a general idea of sketching these things by hand. So let me, I'll carefully label these intercepts. So let me label the intercepts and then the asymptotes first. Okay, so the x-intercept is 1, 0. So I'll put, I'll put 1. I'll put the value of 1 like I don't know. The increment size is up to you. It really is. It's up to you. So I'll put the value of 1 maybe. Put the 1 right there. Actually, you know what? Sorry about that. Let me move that over left one more spot. Let me put the value of 1 right there. Yeah, that looks better. So that's the x-intercept, 1, 0. All right. The y-intercept 0, 1/9. So I guess I could put that slightly. I could put that there. 0, 1/9. All right. So those are my intercepts. Now the vertical asymptote and the horizontal asymptotes, those are vertical and horizontal lines. So I'm going to indicate those on my graph. So -3 and 3. So since that's 1, let me go. So that was a unit of 4 units. So let me go another 4. 1, 2, 3, 4. 1, 2, 3, 4. So that right there will be the start. That right there will be the start of my vertical asymptote, x equals 3. This is almost like an art project. So that's the line x equals 3. That's the vertical asymptote. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So that right there is going to be the next vertical asymptote, -3. All right, so that's the vertical asymptote, x equals -3. All right. So those vertical lines, those dashed vertical lines, they're not part of the graph of the function. Those are basically, you could think of those as like separators or dividers of the graph. Okay. The horizontal asymptote is y equals 0, so that's easy. That's just the x-axis, y equals 0. So the x-axis and y equals 0 are one and the same thing there. The horizontal asymptote is the line y equals 0, which just happens to be the x-axis. So that's the horizontal asymptote. And, that makes sense because I know that 1 comma 0, I said, r of x crosses the horizontal asymptote at 1 comma 0. I said that. So it makes sense that 1 comma 0 is on the horizontal asymptote. And this is a vertical asymptote. And that's a vertical asymptote. Okay. So now that I have my intercepts and asymptotes, now I'm ready to graph my rational function. Okay. So how do I start? Well, a good thing to do is to start with the intercepts. So I could always, I always start from the inside and work my way out when I'm graphing a rational function. All right? That's what I like to do. So I know that my graph is always going to cross a y-intercept. So I know my graph, I can extend from this. I can extend by going this way and this way because I know it's going to cross that. That's a y-intercept. I know that's going to happen. Okay? Now you're probably wondering, well, why don't I do it the other way? Why did I do it the other way? Well, because if I were to do that, I would have to come down to cross this point right here. Okay? All right. So I know that I'm going this way. Sorry about that. I was checking something. I know I'm going this way because I know that when I come down here, right? So I'm going to come close to here's my x-intercept, 1 comma 0. Now, because of the multiplicity, I know what? I know the multiplicity of my x-intercept y crosses at x equals 1. So when I do finally get to when my graph finally gets to x equals 1, what's it going to do? It's going to cross. And it's going to come down. It's going to come down like this. All right? I know it's going to cross because that has odd multiplicity. Which means it crosses. All right? I determined that when I did the multiplicity for that. So when it crosses, it's going to cross that point. All right, so now I'm coming down, right? And now I'm coming down. My graph is coming down. So what is it going to do? Well, it's going to keep coming down like this until, it's going to keep coming down like this until it's going to get closer and closer to this vertical asymptote, right? Now, remember, the graph of a rational function can never cross a vertical asymptote. It can never cross it. So as x gets bigger, my graph is going down like this, but as I get closer to my vertical asymptote, my line is just going to go down. Like, as soon as it gets close to it, it's going to go straight down. So basically, I know I'm not graphing this ideally, but basically what's happening is this. I come through my y-intercept. I cross my x-intercept because it has odd multiplicity. Right? I'm going along until eventually I get near my vertical asymptote, and then I'm going to hug my vertical asymptote all the way down. Okay? So this little dip right here, that just might be because of my sleight of hand, but there isn't a little bend there. It's just me being with a shaky hand. All right. Now, what's going on the other side? Now, remember, the multiplicity of my vertical asymptote plays a role here. X equals 3, right? Multiplicity of my vertical asymptote was odd, right? So because it was odd, that means it's inverted. That means if it's going down on the left side, it's going to be going up on the right side. That means it'll be doing this. On either side of x equals 3, the behavior is going to be inverted, right? It's going to be crisscross. Now, as my function, I'm going to be hugging the vertical asymptote as close as I can, but then as x gets bigger, y is going to get smaller. Now, this is my horizontal asymptote here, so as I get closer to my horizontal asymptote, it's going to level out like this, because the only place it crosses the horizontal asymptote is 1, 0. That's how I know it does this. I know it's not going to go down any further because the only place it crosses is 1, 0. That's the only place it crosses. Now let's go to the left here and see what it does. So my graph keeps going out like this. How do I know it's going up and not down? Because if it were to go down, what would it have to do? If it goes down, it would have to cross the horizontal asymptote. But it can't do that because I already said it crosses the horizontal asymptote in one location, 1, 0. So I know by the process of elimination, it must go up. You can kind of see how all this information plays a role. So it's going out like this, it's going out like this until when I get close to my other vertical asymptote, -3, it's going to get closer to it and closer to it until eventually, when it gets so close, then it's going to go up like that. So that's how you fill in the behavior. That's what's going on between the asymptote, the vertical asymptotes of -3 and +3. That's what's going on there. Now, what's it doing on the other side on the left side of -3? Well, that's the multiplicity of -3. It's inverted. So that means if it's up on the right side, on the left side it'll be down. And it's going to keep going up, going to keep going up, going to keep going up until, what's it going to do? Is it going to go out to the left or is it going to go straight up? Well, it's going to go out to the left. It's going to go out to the left as x gets closer to -infinity, because this line right here is the horizontal asymptote, and it only crosses at one location, 1, 0. So that's how I know that when it gets closer to the horizontal asymptote, it shoots out to the left like that. So using this information gives us an idea of how to graph a rational function. Okay? I knew it extended out like this because it had to cross the x-intercept here, and it's going to keep going up because if it were to go down, it would have to cross the horizontal asymptote over here. That's how I know that when I started this, it was going to go this way, not the other way around. Because if it went the other way around, it would imply it would have crossed it over here, and it would miss this x-intercept over here. That's how I know it went down from left to right, not up from left to right. So I know that's a lot of information, but that is the basic way of graphing a rational function by hand. It's a matter of finding all this information and putting it all together to sketch a rough graph of this rational function. You can graph a rational function in your calculator, but in your TI calculator, it might look a little messy because of technology limitations. So there's your rational function. So if you go to y equals, type in x minus 1 divided by the quantity x plus 3, x minus 3, then you go to graph, there it is. So notice, you're not going to see the vertical asymptotes in your graph. They're not going to show up here. Like those vertical lines, -3 and +3, they're not going to show up here. But here's the behavior to the left, right here. That's this part. The behavior to the right of x equals 3 is right here. And inside, in between -3 and +3, here's the behavior there. It goes down and goes through it, like this. I could zoom in there to emphasize that. There it is. That's the behavior inside those vertical asymptotes. If I go from like -5 to 5, maybe that'll look better. There it is. There's your rational function. And that is somewhat similar to what I have. But that's how you'd sketch it by hand. And there it is. It's a long process, but nevertheless, that's how you would do it. You know, these problems are lengthy. But, you know, this is big boy algebra, so this is big boy and big girl algebra, so, you know, this is algebra. What we're doing here is good old algebra. All right. Let's do another example. So yeah, lots of work, lots of work. All right, factor the function. The numerator is a quadratic. The denominator is a difference of 2 squares. The denominator factors to be x minus 2 and x plus 2. The numerator factors to be what? 2x and x, and 2 means it's going to be 1 and 2. Or it could be 2 or 1, I don't know yet exactly. So 2x and x, that's going to be, yeah, I think it's the other way around. I think it's going to be 2 and 1. Yeah. Or is that a typo? Oh no, I had, you know what, I had it right the first time. I'm just being messy here. I can't even factor. That's how you know you're getting tired. So, all right, the outside here, that would be what? The factors of 2, it's either going to be 1 or 2 or 2 or 1. So this is going to be 2. This is going to be 1, right? Because 2x times 2 is 4x. 1 times x is x. That's going to give you 5x, right? So this is going to be negative and negative, right? 2x times negative 2 is negative 4x. Negative 1 times x is negative x. That gives you negative 5x. Negative 1 times negative 2 is positive 2. The denominator factors to be x minus 2, x plus 2. Okay. Now what happens here is when I factor the top and bottom, what happens? The numerator and denominator, like, they have a common factor here. X minus 2's cancel out. They cancel out. So they don't show up in the function. So my function reduces to be 2x minus 1 over x plus 2. That's what my function reduces to be, which is interesting. Okay. What's my domain? So the domain is what? It's going to be all real numbers except where the denominator equals 0. Which, if you solve that, that's easy. That's x equals -2. So all real numbers except x equals -2. And in interval notation, you could write that as negative infinity up to -2 and -2 to infinity. Okay. Locate the intercepts. X-intercepts when y equals 0. So my function is when 2x minus 1 over x plus 2 equals 0. If you do cross multiplication there, right? Cross multiplication. 2x minus 1 times 1 is 2x minus 1 equals 0 times x plus 2 is 0. Solve that for x. Add 1 to both sides. Divide by 2. You get x equals 1/2. So my x-intercept, my 0, is 1/2 comma 0. So because that is a 0, I'm going to have to determine the multiplicity. Y-intercept is when x equals 0. Just plug in 0 into your function. So when you plug in 0 in here, right, you could plug it in here or here because they reduce to be the same thing. And they reduce to be the same thing. So when you plug 0 in here, you're going to get what? Positive 2 over -4 or negative 1 over 2, which reduces to the same thing. It's going to be -1/2, right? So you're going to have plus 2 over -4, which is -1/2. So my y-intercept is 0, -1/2. Y-intercept, that's the x-intercept. Okay, let's determine the multiplicity of my x-intercept right here. So for x equals 1/2, that comes from the factor 2x minus 1. That's to the first power, right? Since that is a multiplicity of 1, which is odd, that means my function is going to do what at the x-intercept? Crosses. X equals 1/2. Okay. That was the only x-intercept I had to worry about, so. Actually, let me go back to step 1 here. What's the domain of this function? Actually, now that I think about it, my domain would also not include positive 2. Because even though this canceled out, the x minus 2's canceled out, you still can't put in 2. Because if you put 2 in here, you're going to get 0 in the denominator, right? If I just ignore the top for a second, and I put 2 in here, I'm going to get 0 down here, which isn't going to be good, right? So, yeah, I know that the factor x minus 2 drops out, and you get this, which technically only deals with negative 2. But if you look at the original function, 2 or negative 2 won't work. So let me make a note of that here. Note, even though the x minus 2 canceled out, x equals 2 is not part of the domain. So actually, all real numbers except negative 2 and 2. So my domain is really the following. Negative infinity up to negative and 2, negative 2 up to 2, and from 2 to infinity. That's my domain. Sorry about that. And you can see that if you plug in 2 here, you're going to get 0 in the denominator. Doesn't matter what's in the numerator. Now, when it comes to finding a vertical asymptote, there is only going to be one. That's just going to be x plus 2, which gives you x negative 2. Okay, so next page. So locate the vertical and or horizontal oblique asymptotes of the function. All right, so the vertical asymptote is, we already did that work. When the rational function reduces, you get 2x minus 1 over x plus 2. So x minus 2 is going to be the only vertical asymptote. Now, 2 is not part of the domain, but 2 is not a vertical asymptote because there is no factor of x minus 2 down here. That cancels out. So, yeah, while 2 may not be part of the domain, it's not a vertical asymptote. The only vertical asymptote occurs when I have x plus 2 equals 0, which gives me x equals negative 2. That's the only vertical asymptote. Okay. Now the multiplicity of this vertical asymptote so x equals negative 2 comes from the factor x plus 2. The power of that is 1, which is odd, which means r of x does what? It's inverted on either side of that vertical asymptote. All right, now let's find the horizontal asymptote. So if I look at my function, right, the degree of the top is 2. The degree of the bottom is 2. They're the same. So that means what? That means my horizontal asymptote is the line y equals what? It's the ratio of their leading coefficients. The leading coefficient of x squared is 2 over the leading coefficient of the x squared in the bottom is 1. 2 over 1 is just 2. So my horizontal asymptote is the line y equals 2. All right. determine if my function crosses the horizontal asymptote. Does it? How do I know? Set R of x equal to your horizontal asymptote. So my function is what? It reduced to be 2x minus 1 over x plus 2. It reduced to be that. So set that equal to my horizontal asymptote, which is 2. Solve that. Cross multiply. So 2 times the quantity x plus 2 equals 2x minus 1, this is over 1, 2x minus 1 times 1, which is just 2x minus 1. Distribute the 2 here, you're going to get 2x plus 4 equals 2x minus 1. If I solve that for x, well, subtract 2x from both sides. Uh-oh, the x's drop out. So you end up getting 4 equals negative 1. Well, that doesn't make any sense. So because I didn't get a true statement, because this doesn't make any sense, R of x does not cross the horizontal asymptote. So it won't cross the horizontal asymptote in this case. Okay. We determine the intercepts, we determine the multiplicity of the x-intercept, we determined the vertical asymptote, the horizontal asymptote, we determined the multiplicity of the vertical asymptote. I think we're ready to sketch this sucker. So, so let me write down the information. Right, and it factors down to be, right, if you factor it, we did this in step 1. The x minus 2's cancel, so you're left with 2x minus 1 over x plus 2. So really I'm graphing this function. So my x-intercepts were what? 1/2 comma 0. That was the only x-intercept. And the multiplicity there was odd, right? Which means it crosses x equals 1/2. All right. The y-intercept was 0 comma negative 1/2. There is no multiplicity for the y-intercept. The vertical asymptote was x equals negative 2. The multiplicity of that was odd. Which means R of x is inverted on either side of that vertical asymptote. The horizontal asymptote is y equals 2, and we know that it doesn't cross. Y equals 2, because we did that in number 4. Alright, so that's a lot of information. That's all the information we did, really. So let's put this all together and graph this sucker. So the first thing you do is plot the intercepts and then the asymptotes. All right, what are my x-intercepts, y-intercepts? X-intercept is 1/2 comma 0. So if I went in increments of 4 for 1, right, 1, 2, 3, 4, that was 1, then that will be 1/2 comma 0. That's my x-intercept. My y-intercept was 0 comma negative 1/2. So that's going to be what? Right here. All right, those are my intercepts. My asymptotes, my vertical asymptote is x equals -2. So 1, 2, 3, 4, that's 1. 1, 2, 3, 4, that's 2 right there. So that right there, that vertical line is the value of the vertical asymptote, which is x equals negative. That's the vertical asymptote. My horizontal asymptote is y equals 2. So 1, 2, 3, 4. 1, 2, 3, 4. So right there. So the line so that line y equals 2 is the horizontal asymptote. And I know that it doesn't cross y equals 2. I know that. All right, so I labeled my intercepts and my asymptotes. So now I'm ready to graph this thing. All right, so I like to start from the inside and work my way out. I know that the y-intercept gets crossed, okay? And I know going from left to right, it's going to be going up like this because I have to cross this at some point. Remember, this is odd multiplicity. So it means it crosses. Right? All right, so I know from left to right it's going up like this. I know it's doing that over here at least. And it's going to cross, let me go to the right. So it's going to cross 1 comma 0 because the multiplicity there was odd. All right. So now I'm going to keep going. Going to keep going, going to keep going up, going to keep going up, going to keep going up. But as I keep going to the right, and my function keeps going up, I know that my horizontal asymptote, it's going to approach my horizontal asymptote, right? But we know that it's not going to cross that horizontal asymptote. We know that. We verified that earlier. So as it gets closer to the horizontal asymptote, what's it going to do? It's going to hug the horizontal asymptote. It's not going to cross it. It's going to do that. We know that just by, we verified that earlier. All right, let's go over here now. So as I keep going to the left, I know I'm going to keep going down. I know it's going to keep doing this because if I were to go up, what would it have to do? If it were to go up like this, it would have to cross the x-axis at some point. But I know that's not going to happen because I only have one x-intercept and it's over here. So it's not going to do this. It won't do that. It can't. This single x-intercept over here prevents it from doing that. So it's going to keep, so I know it's going to keep doing this. And it's going to keep going until what? It gets closer to the vertical asymptote of -2, which it'll never cross. So as it gets close to it, it's going to get so close that then eventually it's going to go straight down. It's going to hug it, but it'll never cross it. All right. Now, to determine what's going on the left side of this vertical asymptote -2, that was the multiplicity of the vertical asymptote. It was odd multiplicity, which means it's inverted. So So that means since it's going down on the right side, it must be going up on the left side. That's how I know it's doing that, because of the multiplicity of my vertical asymptote is odd. Now, it's going to keep coming down, but what's it going to do? Is it going to shoot out to the left like this, or is it going to go down like this? Is it going to go down and shoot out over here? What's it going to do? Well, here's my horizontal asymptote, the line y equals 2. I know it's never going to cross that. I verified that earlier. So because of that, it's going to come down until it gets close enough to the horizontal asymptote. It can't go to the right, it can't cross the vertical asymptote. It can't go down because it can't cross the horizontal asymptote either. So it has no choice but to shoot out to the left like this forever. So as it comes down, it's going to shoot out like that towards negative infinity. And that right there is the graph of my rational function. So, you know, graphing it is okay. It's just, you know, it can take a little time to do, but, you know, graphing it is not that much, it's really not that big of a deal, to be honest. So that right there is the rough sketch of my rational function at the start of this problem. It's a long process, I'm not going to lie. Actually, I forgot one little piece. It's a small thing, don't worry about it. It's not a big deal. So remember at the beginning of this problem how I said 2 is not part of the domain? Right? So what's going on at x equals 2? So remember, that factor cancels out. All right, the x minus, you know, that cancels out, and you get left with this. But what's going on at x equals 2? If you plug 2 in here, so you're going to get 2 times 2, which is 4. 4 minus 1 is 3. And 2 plus 2 is 4. So at x equals 2, you get this. So you actually get the order pair 2, 3/4. So because this point canceled out, you know, if you put 2 in here, you're going to get division by 0, which you can't have. But because it drops out, that point has a hole. You know, this point is not included in the graph. There's actually a hole here. Because the x minus 2's cancel out. They cancel out. So actually at this point, 2, 3/4, there's a hole in the graph. So if I go out, this is 1/2, that's 1, 1/2, that's 2, and then 3/4 is right. So right here, so this point right here has a hole at that. There's a hole there. That's the point, 2, 3/4. Sorry about that. Whenever you have something cancel out like that, whenever you have a factor that cancels out, you're going to have a hole in the graph. So let me make a note of that here. Note. Whenever a factor cancels out of r of x, comma, you'll have a hole in your graph. So whenever a factor cancels out of r of x, you'll have a hole in the graph of r of x. That will happen. So you're going to have a hole there. So what you have there is something like this. That right there is the graph of the rational function. So that was a little minor detail that escaped my attention, but I know it seems like a lot, but you know, if you forget to do that little thing, which is easy to do, obviously I did, but so this is like an exception to the rule. If you have a factor that cancels out, you'll have a hole in the graph at that point. But, you know, that only occurs in special cases, like when that happens. Okay, so that right there is your graph of that rational function. There's a hole there. All right. So the last kind of problem you could see here is building a rational function from a word problem. So this metal company manufactures aluminum cans in the shape of a cylinder with a volume of 500 cubic centimeters, or 0.5 liters. Same thing, different units. The top and bottom of the can are made of a special aluminum alloy that costs 5 cents per square centimeter. The sides of the can are made of a material that costs 2 cents per square centimeter. All right. So in this problem, I want to express the cost of material for the can as a function of the radius of the can. So I want to find an independent and dependent variable. So my independent variable is going to be r, which is the radius of the can. And the dependent variable is the cost function. So we could call that C. That's the cost of material. For the can. Alright, so what I'm really going to be doing is I'm going to find a cost function. And find the cost as a function of its radius. And that's what I want to find. Okay, well, let's pick apart this information. So the types of formulas, I'm dealing with a geometry problem, right? I'm dealing with geometry. So here's a cylinder, right? And I'm trying to find a function that measures the cost of the material as a function of its radius. So if you have a can, right? If you have a can and you were to unravel the can, if you were to roll it out, you would get a sheet. That's what's going on here in this picture. So this sheet has a surface area. Yeah, that sheet has a surface area. And the area, so the length of this sheet is actually the circumference of the circle, which is 2 pi r. That's the length of that sheet. It's the circumference of the circle. So if you think about it, you have a circle, right? And if you roll it out, you're going to get the sheet. You're going to get the length. You know, the circumference of this is the distance around the whole circle. So if you cut it and then you lay it out, you're going to get the length. That's the circumference. The circumference formula is, you know, circumference is equal to 2 pi r from geometry. So that's where that comes from. And then this part right here, well, that's the height of the can. Right? The circumference is when you cut it, but then, you know, if you look at the can in a vertical direction, you're going to have a height. Right? So to find the area of a rectangle, you just take the length times the width, which in this case will be, so the area is going to be the length, which in this case is 2 pi r, times the width, which in this case is h. So the area of the can is 2 pi r h. And that's why you see it right there. The area is 2 pi r h. All right. Now the top of the can, so the tops of the cans, the top and the bottom, they're circles. Okay. Well, that's easy enough. So the area of the top, is just a circle. Well, that's, you know, the area of a circle is pi r squared. The area of the bottom is another circle, which is also pi r squared. So what's the area of the top and bottom together? Well, you just add the area of the top circle and the area of the bottom circle together. So when you add that together, you're going to get, so pi plus r squared plus pi per r squared is, so the area of the top and bottom is going to be 2 pi r squared, right? So let me write that down here. The area of the top and bottom is just pi r squared plus pi r squared, which is 2 pi r squared. So the area of the whole can, is the area of the top and bottom, which is 2 pi r squared, plus the area of the interior of the can, the lateral surface area, right? If you cut the can in half, if you cut it down with a pair of scissors and roll it out, you'll get a nice length, which we already found to be 2 pi r times h. So this right here, this little formula, 2 pi r squared plus 2 pi rh, that's the area of the whole can. Now I'm trying to find a function that measures the cost of the material for the can, not for the area. So how do I find the cost to manufacture the can? Well, if I take the cost of the material times the area, I will get the cost to construct the top of the can and the bottom of the can. So that problem is given to us. So that information is given to us. So the top and bottom of the can are made of a special aluminum alloy that costs 5 cents per square centimeter. So this is the area, right, of the top and bottom. And the top of the bottom costs 5 cents per square centimeter. So if I multiply this by 0.05, that'll be the cost to manufacture the top and bottom of the can. So the cost of the whole can will be, so this is the area of the top and bottom of the can. I'm going to multiply that by the cost of the top and bottom of the can, which is 0.05 cents. So that's going to be 0.05 times 2 pi r squared. That's the cost of the top and bottom of the can. Plus, now what's the cost to manufacture the surface area, the interior part of the can? Well, the sides of the can are made from material that costs 2 cents per square centimeter. So that right there is the cost that you would multiply by the lateral surface area of the can. So 0.02 times 2 pi RH. So this is the cost of the top and bottom. And this right here is the cost of the side of can. This is the top and bottom of can. All right? And you add them together because that would give you the cost of the whole can. All right. So we're one step closer to finding our cost function to manufacture this can. Because we're trying to find that function as a function of r. So if I do a little simplification here, I'm going to get what? C of r. So 0.05 times 2 is 0.1. So when I just did that, so I'm going to get 0.1 times pi r squared plus 0.02 times 2 is 0.04 times pi RH. I just multiplied 0.05 times 2. I made that look nicer, and 0.02 times 2 make that look nicer. Now, what's the problem here? There's one little problem here. One minor problem. So, if you look here, this cost function is supposed to be a function of r. But what variables do I have in here? I have r, but I also have h. Now, pi is not a variable. Pi is a rational number. All right. So I have two variables in here, but I need this to be a function of r, not just r and h. So how am I going to take care of that? I need to substitute another value in here to get rid of that h. So how do I do that? So my function needs to be a variable with r only. Right now I have r and h in there. So I have to get rid of the h. I have to replace h with an equation in terms of r. So how do I do that? Well, if I go back to there's one more piece of information I could find about this problem. And it has to deal with another formula. Aluminum cans are in the shape of a cylinder with a volume of 500 cubic centimeters. So the volume of a cylinder, I need to use that formula. So the volume of a cylinder which I'm having difficulty recalling at this particular moment because it's late at night. I think it's 4/3 pi r cubed, but I could be wrong about that. No, that 4/3 pi r, that's the volume of a sphere. the volume of a cylinder is pi r squared h. Okay. The problem says that the volume is equal to 500 cubic centimeters. So what I'm going to do is I'm just going to set this equal to 500. And if I solve that for h, you get h equals what? You're going to get h equals 500 over pi r squared. So I'm going to take that and I'm going to replace h here with this. So when you do that, you're going to get 0.1 times pi r squared plus 0.04 times pi times r, and h now becomes 500 over pi r squared. So when you simplify that down a bit, I'll write it here. The cost as a function of its radius, 0.1 pi r squared. So 0.04 times 500 is 20. So it's going to be plus. Now pi over pi, they're going to cancel. And r over r squared, that's going to cancel, but the r will be in the denominator. So that'll be plus 20 over r. So when it's all said and done, that right there is my cost function, because that just contains the variable r, which is what I was aiming to do from the get-go. Use the formulas that they give you. This is the surface area of the whole can, the top and the bottom, or top and the bottom and the sides. The cost is multiplying the top by the cost, the top and bottom by the cost, and the sides of the cost. And since I need a function in terms of r only, I had to use the volume, which is equal to 500. I had to use the volume of a cylinder formula and then replace h with that. Do a little simplification. 0.04 times 500 is 20. The pi's cancel. R over r squared is 1 over r, which is just 20 over r if I keep the 20 in the numerator. So that right there is my cost function. Yeah, a lot of work there to just get a cost function as a measure of the radius. So graph that using your calculator. Okay, let's graph it. So 0.1 pi is right there. So pi x squared plus the fraction 20 divided by x. Graph it. I may have to adjust that. So there is my, oh, the top is cut off there. Let me zoom out a little bit. Actually, that might be better. There we go. So there's my graph of my rational function, or here's my graph of my cost function. All right, what value of r will result in the least cost? Well, let me ask you this. Which part of this function do I not care about? Which part don't I care about? I don't care about this part over here. Why don't I care about that part? Because that would, if it's over here, that would mean r is negative, right? If I go to the left, and this is a function of r, that would mean r is negative. But why don't I care about that? Because I can't have a negative radius. That's not possible. So the only part that I care about is this part over here. The only part I care about is this part right here, which kind of looks like this. All right. I don't care about that part because it's negative. Well, that would give me a negative r value, which can't happen. You can't have a negative radius, otherwise you don't have a can. So what value of r will result in the least cost? So you're just going to find the local min of C of r. So you know how to do that in your calculator. That's this point right here. That's the local minimum. So second, calculate minimum. Go to the left of that point, which is right. That's good enough. Go to the right of that minimum. Enter, and I get 3.17, 9.47. Approximately. That's my local minimum. So the local min of CR is the order pair 3.17, comma 9.47. If I round it to the second decimal place, just read that off. So what's the least? So what value of r will result in the least cost? So my radius, right? Because this value, this coordinate right here, that's the radius. So a radius of r equals 3.17 will generate the least cost of making the can. What is the least cost? Well, the least cost is just the y coordinate of the local minimum. So the least cost will be $9.47 because the units of money here are cents per square centimeter. So the least cost will be to manufacture the can with a radius of 3.17 would be roughly $9.47. So yeah, that word problem, there's a lot there. Not gonna lie, a lot in that word problem. Rational functions, there's a lot to them. There's an absolute lot to them. A lot of information to consider. They take time. So, yeah, I know there's a lot to this, but hopefully you are following when watching this video. But so there's a lot of going on when you're dealing with the graph of a rational function. This was a long section. Alright. So yeah, there was a lot going on here, but that takes practice and time, but that is the end of this section, and I think there's one more section in chapter 5, so that's the end of this video.